Hello everyone. In this video, I'm going to show you how to build a PetaLinux system on top of a Zynq 7000 Xilinx MP sock. You can also build it on a Zynq UltraScale Plus. The steps are the same, except one minor tweaking when we modifying the file. But in this demo, I'm going to use the ZC706 evaluation board. Before we start, we need the Vivado installation. I'm using 2020.2, and you also need the PetaLinux installed in the Linux machine. So first of all, we need to build the hardware, which contains the Zynq processing system and the necessary accessory. We will use block diagram flow. So create a block design. We also add the GPIO module to control the LED for demo purpose. So the basic hardware system, just like that, very simple, and the ASIC address is 4120. We can verify the design. Should be no problem. And then now we need to generate a wrapper and make it as a top file. Because we start the project from the board file, so all the I/O pins are already mapped properly. We will just wait the IP to generate the output files. Now we can generate the bit stream. Okay, now we can export the bit stream to a hardware description file. And then we copy that description file to the Linux machine and move on to the Linux. As you can see, the bitstream size is 13 megabyte. The ZC706 flash memory is only 32 megabytes. So we're going to rerun the build and compress the bitstream. We can open the implemented design and change the settings of the bitstream. So we can enable the compression. Then regenerate the bitstream. The configuration of the bitstream are saved in the constraint file here. Now we can take a look again. So the bitstream size is compressed to 1.4 meg only. Now we can export again. And move on to the Linux. Okay, now we moved on to the Linux system. The Linux we are using is Ubuntu 18.4 because the Vivado and PetaLinux 2020.2 only compatible with 18.04 Ubuntu. Or other Linux distribution, you can check the Xilinx documentation. Before we are going to create the PetaLinux project, we first need to set up the PetaLinux environment. After installation, there's a setting script that can create the PetaLinux environment. Now we can create the PetaLinux project folder. The template we are going to use is Zynq because we are using ZC706, the Zynq 7000. If you are using the Zynq UltraScale Plus, you're going to use the template as Zynq MP. So inside the text project folder, we are going to create the PetaLinux project subfolder. First of all, we need to grab the hardware description. Remember the hardware description files we copy here. The desired one wrapper description. We will try to use the flash memory as the placeholder for the image. So for that purpose, we're going to configure the PetaLinux. We're going to configure the subsystem hardware. The bootable image, first of all, we need to set the boot image to primary flash. And then we set the kernel also to primary flash. Then we need to configure the flash address range. There's a partition, first of all, the boot partition, the size, because the bitstream is 1.4 megabyte plus the bootloader. So everything together, we just assign 4 meg for that. There are also 2 partitions for holding the boot script, so we just make this slightly smaller. The boot environmental also, that's 200K, that's okay. And then the next partition, we're going to put the boot script. The size is also 200 meg. The next partition will be kernel. For demo purpose, later on we are going to build the web server, so the kernel will be kind of big because we need to put something on the root file system, so we just reserve a little bit more space for that. For that size, we're going to put, that's 19 megabyte. And on top of that, we need to also put another root file system. The size of that, there's a total 32, so we reserve the rest 9 meg. So basically, there's 4 megs here, 19 megs here, and 9 megs here. Okay, then we save, exit. Everything else should be normal. That's all. Now we're going to configure the U-boot because we change the boot script starting position. The U-boot by default is setting the boot script position in FC00 somewhere, so we have to change that. So after like 10 minutes, the system build the U-boot and then show up the menu for configuration. So under the ARM architecture, there's a boot script address where by default boot script offset where by default is set to FC. So because we are putting that in the flash under at the 3C plus 2 CE, so we can do change that. Save this. Everything else should be good. So the configuration has been saved to here. Project spec component Yoto workspace source U-boot under the local files. So this has been set. You can also see there's a new file created under here. Project spec meta user BSP. You put this one. So there's some definitions showing where's the QSPI size offset, blah blah blah. So because we are using the Zynq and the kernel offset here, actually we put 4, and the RAM disk offset here is actually 4 plus 13x, so it's 17. The net here size is 130. RAM disk size is 900. Okay, so the QSPI kernel size offset. If you're doing, the only difference between the Zynq 7000 and the Zynq UltraScale MP-SoC is that if you use Zynq UltraScale, you need to change these settings here for the Zynq MP. And one more thing is the fit image size, which is the kernel size 13000. So the two settings here, I don't know which one, but basically if you set both, there's no problem. That's all. Save that. And then we can build the PetaLinux. Oh, before that, because we are doing demo for the GPIO and the web server. The web server is actually under the Busybox package, so we're going to configure that. We'll change the root FS settings. So under the apps, the GPIO demo, we're going to need that to control the hardware on the LED. And then under the file system package base, there's a Busybox. So we will enable the HTTP server so that we can make the Zynq as a web server. The root file system settings are saved here. So as you can see, HTTP is enabled. The GPIO demo is also set here. Now we can build the PetaLinux. So after the PetaLinux is built, some image files are created here. So the boot screen, the U-boot image, and the root file system. Then right now we need to package the PetaLinux into a boot.bin binary file so that it can load into the flash. So we're going to package the boot, and first bootloader is image. The first bootloader image is the Zynq FSBL here, and then we'll load the U-boot image. The U-boot image is the U-boot elf here. Then we need to load the FPGA bit file. The system.bit is the compressed bit file we create under the Vivado. Then just need to force the build. Okay, make sure boot, first boot, U-boot image. Yeah, that's all. Then the system will combine 4 files: the first bootloader, the boot.bit, the system.bit, the U-boot file, and the system configuration into the boot.bin, the binary file, which is created here. So for now, we can load these 3 files into the flash. We just create a new folder here to host the file. Because the file name extension is the binary, this one is not, so this two needs to be renamed. So make sure I'm not screw up the file. I just place them here and change the file name and also change the file name here. Now we can use the Vivado to load the file. So for loading JTAG to the flash, you need to configure this to be JTAG mode, then turn on. So we need to add the flash chip. For the ZC706, it's QSPI by A dual parallel 1.8 volt. So we can now we load the boot bin first. At RGS offset 0, we need to define the bootloader. So just make sure configuration file only erase program and verify, okay? Next, we will need to program the boot script at the RGS of 3E because the boot image is 3C and then 20K of the environment. The same bootloader. Make sure also configuration file only. You can erase program, verify everything. The last one, we need to program the boot image at the RGS of 4 meg. So everything looks fine. And then we can turn it off and boot from the flash. So make sure the dip switch setting, then you can boot from the flash. You can see it's programmed. So right now we can open PuTTY as a serial terminal. The settings will be at the TTY USB 0 of the Linux system, and then 115K baud rate. So as you can see, the system is here. You can boot the system. So to be clear, we can just reboot and see the boot log file. So as you can see, we changed the ARM architecture put script address to 3E here. So it put from the device offset 3E, and then it load the boot image from the 40 here. So everything works fine. Right now we can do some GPIO demo for this build. The GPIO demo is a built-in app for using the GPIO. We first need to know where is the ASIC GPIO device we put in. So the GPIO device can be found here. As you can see, the two GPIO chips, the highest one, highest one, is the one defined in the first on the device tree. So we have only one. That's why we use this 10.0 as the GPIO. So to control the LED on the ASIC GPIO device, we're going to do GPIO demo. G is the device. Output, that should turn on the LED, and put it back to 0 should turn off all the LED. Or you can do one by one. Also, you can see the Ethernet is available on the board. ETH to 0, but there's no IP associated to it. We can associate some IP. For example, 10.10.10.2. Okay, and then the local Linux here, we can also associate IP for the same range. The device is the ENP4S0. ENP4S0. You can associate 3, for example. Now you can try ping the Zynq board, and also from the Zynq board to ping the Linux. All looks good. And we enable the Busybox Web Server, so we can try look at what's on there. And seems like nothing is available in the web server because the web file is hosted here. So you can see there's nothing there. So next step, we're going to put some web pages in this folder, and we'll go back to use Firefox to see what's going on there. For that, we will need to go back to rebuild the PetaLinux. So, as you can see, in the already built package, there's a root fs folder, which let's just extract here. Take a look. As you can see, in this folder there's nothing. Then previously I have made just the index.html. Basically show some text and then query the time and date, and then refresh every 5 seconds so that you know the evaluation board is running. So we can paste this file into the root.fs project. Now we need to instruct the build to use this folder as the root.fs default system. To do that, we need to go back here. We need to configure the kernel to make the this folder as the root.fs system. We will indicate the full path of the folder. So under the general setup, there's an initialize RAM file system setting, and then the source files. Basically, you can specify specify the whole folder as the root file system. Save that. And this configuration saved in here. Local file. So the configuration is good. And then we make sure the root file system configure didn't change. The root file system base Busybox still there, app GPIO still there, and then we need to make sure the U-boot, the ARM architecture is not changed. Make sure the boot script offset is still okay. So this is still here, 3E. Now we're going to rebuild the package. And finished. Let's see what has been built. As you can see, the boot image, the U-boot image is larger because it contains the extra root file system. Now we just repackage the boot.bin. The U-boot image just barely fit in what we assigned 19 megabytes of the flash system. So we copy these files again. This file actually didn't change, so we just do this too. And remove this. Rename this. Now we are going to reprogram the flash on the board. Again, program the boot.bin, start from 0. The boot script didn't change, so just leave there. And then reboot the system. Now we can go to see the files there. So we can it's connecting. Now go back to the Firefox and see what's going on. There you go. The web server is there. So if you are interested, you can make more complicated web service here. My next project probably we're going to use the programming logic side to capture some image and then trying to show some image in the web server. See how I can do that. Other than that, the ZC706 board has no much external connections unless you have the daughter board. Otherwise, the board itself Ethernet is the most useful external connection, so that's why I built the web server here. And pretty much that's all for this video. Hope you enjoy. See you next time.